Hi, everybody. I hope you're all feeling well-rounded and appropriately polar because today's video is polar coordinates as opposed to rectangular coordinates that we're probably much more used to and which are, pointy and square and not round and circular and smooth the way that polar coordinates are. So, how exactly do polar coordinates work? Well, the thing is, coordinates are really directions for how to get somewhere. So what rectangular coordinates, like if I gave you a point 3 comma 4, what that really meant was go 3 to the right and 4 up, right? It was directions on how to start at the origin and go somewhere. Now, for those of you who are in Lubbock or near Lubbock, this makes perfectly good sense because in Lubbock, because the roads are all perfectly straight and they all run north to south or east to west with very few exceptions, it's super easy to give someone directions because you just say, you go 3 streets up and 4 streets over, or you can tell someone that that you're at Fourth and Elgin, and everybody knows exactly where that is because everybody knows the way the streets work. They're all straight up and down and left and right. But polar coordinates are as the crow flies directions. They're like how you'd give somebody directions if everybody was flying around in a helicopter. So for example, the point 3 comma pi over 4 in polar coordinates means you fly a distance of 3 units in the pi over 4 direction. And of course, just like we did when we were learning trigonometry, we measure angles starting from the positive x-axis and moving around counterclockwise. So the picture starts here, right, at 0 degrees, and we move around this way to get to pi over 4. If your trig's a little rusty, it might be a good idea to review that handout on trig facts to make sure that you're cool on trig. Because remember, 0 radians, of course everything will be in radians, that's the way to do things, is pointing in the positive x direction. Pi over 2 is straight up. Pi is to this way, to the side. And 3 pi over 2 is straight down. Of course, 2 pi takes us back to 0 where we started. Well, if you think about this for a second, um, cosine of theta, cosine of my angle, right, would be, in this case, x over 3. 3 is the hypotenuse. X is the adjacent. So if we needed some conversion formulas to turn polar coordinates into rectangular coordinates, then we could get those because we move the 3 to the other side of the cosine, and we get x is 3 cosine theta. In general, 3 is the radius, the distance from the origin. So you would have x is equal to r cosine theta. And of course, y would be r sine theta. Again, how can I tell that? Well, sine is always the opposite, the y side, over the hypotenuse, the r. If we know x and y, we need to turn back into r's and thetas. Well, you can always find r from the Pythagorean theorem. R is the square root of x squared plus y squared. And theta, well, we've written inverse tangent of y over x. That's almost right. I mean, the tangent will always be the opposite over the adjacent side. The thing about this is a little tricky is you have to be careful when you plug this into your calculator, for example, because if you plug, say, 1 and hit the inverse tangent on your calculator, so inverse tangent of 1, it will give you an answer where x and y are both positive, and it'll give you pi over 4 in the first quadrant. But there's another angle whose tangent is pi over 4. That's in the third quadrant where x and y are both negative. So you have to watch it. If your x side is negative, you actually want an answer in the third or the second quadrant, and you may have to adjust your angle accordingly if you punch this into your calculator. Now, there's lots of different notation for polar coordinates. What our book will use is notation looks just like regular Euclidean coordinates. In other words, parentheses r comma theta parentheses. The problem with that is it's hard to tell whether when you see something written as 3 comma pi over 4, whether you mean that as a polar coordinate point or a rectangular coordinate point. The pi over 4 might tip you off that you're thinking about polar coordinates, but doesn't necessarily have to be that way, right? 3 comma pi over 4 could be x is equal to 3 and y is pi over 4. So it's not exactly obvious. So there are lots of other notations people use. The little angled line there, or the CIS, is popular, especially in physics books. In some sense, the right way to do it is r e to the I theta. And this is the real way to do it. But explaining why that's true requires us to talk about sequences and series, which we will eventually do, and that will make much more sense eventually. But for right now, it's less so. And so books usually don't use that notation in Calculus 1 or Calculus 2, but they will in more advanced classes. Okay, now for some warnings. There's a problem with polar coordinates that you don't have with rectangular coordinates. That is, there are lots and lots and lots of names for the same point. So all three of these ordered pairs that I've written there are actually directions, coordinates, for the same point. So 3 comma pi over 4 means head off in the pi over 4 direction and go 3 units. But so does negative 3 comma 5 pi over 4, because 5 pi over 4 is actually pointing in this direction. It's 45 degrees, pi over 4, right? But in the third quadrant. It's exactly the opposite direction. But we say negative 3 is our distance, which means we fly backwards while pointing in the pi over 4 direction. So if I'm facing the pi over 4 direction and I fly backwards, I end up at, well, 3 comma pi over 4. What also happens is I could go 3 positive units, but go 9 pi over 4. That means I start here on the positive x-axis with theta equal to 0. I go around past pi over 2, pi, 3 pi over 4, 2 pi, which of course would be 8 pi over 4. Then go one more pi over 4 to get to 9 pi over 4, and I end up at the same place. Because what I've done is gone around a whole loop before I finally went my pi over 4 angles. So that makes working with polar coordinates a little bit tricky. Also, 0 comma any angle will always be the origin. When r is 0, it doesn't matter the theta, you'll always get the origin. So sometimes solving equations will be a little trickier to make sure we always find all the places where curves intercept. They might meet at the origin with different angles. Okay, so here's some graphs that we could look at. What about the graph of r equals 3? Just r equals 3 by itself. Well, r is always 3. The angle could be anything. So what we get is a circle with radius 3. The analogous sort of thing is, what if we look at the graph of theta equals pi over 4? So theta is pi over 4, but r could be anything. So we have the direction pi over 4, and r could be anything. Notice that it is a line, not just a line segment. In other words, it starts here and heads off in the pi over 4 direction because r could be anything, but also, well, r could be anything, so r could be negative. So we get this part of the line also. Another good practice example is something like r equals theta. So this is a good example of the right way to think about polar graphs. So we start out thinking of r, or thinking of theta as 0, and then see where that takes us. So when theta is 0, of course r will be 0. So that means we start out at the origin. If theta moves around to pi over 2, r will be pi over 2. So it's increased as it's swung out a little further. As my angle sweeps around from pi over 2, which is straight up, all the way to the left at pi, r will then get a little bit bigger from pi over 2 all the way to pi. So what we do is we sweep out a spiral. And this is a really good example to think about how we're going to graph these things. We sort of start pointing in the 0 direction, right? And I plot my point 0, 0, because when theta is 0, r was 0. But imagine that we're sweeping around this way. As theta increases, so does r. So when theta gets to pi, we're all the way over here with r equal to pi. When theta is 3 pi over 2, r's gotten even bigger. By the time we come back to theta equals 2 pi, well, it's the same angle as 0, but the r is different. The r is now 2 pi. It's way out here. And then by the time we get all the way up here, we've gotten even bigger still. So if you've seen like old World War II movies where they show radar screens and you see the little incoming flight of Nazi bombers, and the people are sweating in the bunker, looking at the little radar screen, and you see the arm go around, beep, 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 as it goes around, and every time it passes over the bombers, beep, beep, as it goes around and around and around. That's the picture you want to have in your head of how to draw things in polar coordinates. What we really have is a radar arm with a pin on the end. And the length of the radar arm is r. And as we swing it around, changing our theta, it draws the picture of the graph. So let's do some more examples. So this is r equals 4 sine theta. This is a much better example of the kind of things that we'll actually see in the homework. So the first thing to do when you run across these kind of problems is to do what we did when we first learned how to graph things in, like 8th grade. We plot points. So I'm going to make a table here with r's and thetas, and we're just going to plot points with these. It also kind of helps to think about what sine does. So one way to remember this is I think of it this way. Sine starts out at 0 and cosine starts out at 1. In other words, if you have sine of 0, you get 0. And then of course it changes from that, right? It goes up to 1 when you get to pi over 2, comes back down to 0 when you get to pi. So if I plug theta equals 0 into here, I'll have 4 sine of 0. Sine of 0 is 0, so I get r equals 0. Next, theta is pi over 2, let's say. If I plug pi over 2 into here, sine of pi over 2, well, that's increased all the way to 1, so I get 1 times 4, which is 4. If I try pi, well, sine of pi is back to 0 again, so r is equal to 4 times 0. At 3 pi over 2, sine has dropped to negative 1, so I'll get negative 4 for my r. And by the time I get back to 2 pi, then sine of 2 pi is 0, so r's back to 0 again. So what in the world does this thing look like? Well, let's sort of imagine before I reveal here. When theta is equal to 0, r is 0. As I swing my radar arm around, theta gets larger. Eventually the r gets up to 4. But then, so by the time I'm pointing at pi over 2, which of course is straight up, r is equal to 4. Now my radar arm turns to the side and starts to point to the left at angle pi. R's drop back down to 0 again. So as I swing my arm halfway around, right, my arm starts out at 0, then it lengthens to get to 4, then it shrinks again back to pi. So I end up with a circle. So draw it or imagine as I swing my arm around. When theta is pointing in the 0 direction, r is 0. But as I increase my theta, so does my r increase until finally, when my theta is pi over 2, pointing straight up, my r is 4. But now, as I increase my theta between pi over 2 and pi, my r has to shrink, because by the time I get back to an angle of pi, my r has shrunk all the way back to 0. Now, you may be wondering, you got that whole picture and you just went halfway around. Shouldn't there be like another big circle down here to make a snowman or a figure 8 or something? The answer is, well, no, because look at what happens to the sine. So once I get pointed into the third quadrant here, right, my r is supposed to go from being 0 to being negative 4, right? Well, what's negative 4, right? That means I go backwards. So if I point in the 3 pi over 2 direction, straight down, but I go backwards, that means I'm going to end up back up here on the picture I've already drawn. So what actually happens is, while I'm in the third quadrant, my angle is pointing down here, but my r is negative. So I go backwards and I redraw this first part of the curve. So that by the time I'm at supposed to be pointing straight down, but my r is negative 4, so I'm back up here. The same thing happens. I sweep out the same part of the curve again while my angle is in the fourth quadrant, because again, I'm going to have r's that are negative, so it draws it backwards. This is a useful graph to remember because graphs of circles like this will show up very often in our homework. So next up is a cardioid. We'll see why we call this sort of thing a cardioid in a second. But we make our same table again with r's and thetas. So if theta is equal to 0, well, now I have to plug 0 into cosine. Cosine starts off at 1, so cosine of 0 is 1. But that's in a parentheses with a 1 minus cosine. So I get inside the parentheses 1 minus cosine 0, which is 1 minus 1, which the whole parentheses turns into 0. So my r will be 0. When theta gets to pi over 2, cosine of pi over 2 is 0. So in parentheses I have 1 minus cosine of pi over 2. That's 1 minus 0. So that parentheses becomes a 1. So r becomes 2 times 1, which is 2. Then when I get to pi, so I'm pointing straight to the left, cosine of pi is negative 1. Oh, wow. So the parentheses becomes 1 minus negative 1. That's really 1 plus 1. So the parentheses becomes a 2. When I multiply by the 2 outside, I actually get 4 for my r. Then back to 3 pi over 2. That's where cosine is 0 again. So I have r equal to 2. And at 2 pi, my cosine is 1, which means r is back to being 0. So my graph ends up looking like this. Okay? And why is that? Well, let's imagine tracing this out. When theta is equal to 0, so pointing in the right direction here, then r is equal to 0. So I'm actually at the origin. Now, as I increase my theta, the r increases from 0 to pi over 2. Sorry, from 0 to 2. By the time I swing around a little further, my theta increases from pi over 2 all the way around to pi. My r reaches all the way around to 4. Then as I go from an angle of pi to an angle of 3 pi over 2, the r decreases back to 2. And finally, in the fourth quadrant, as I go from an angle of 3 pi over 2 to 2 pi, my my r decreases back to 0. So why do you call this a cardioid? Well, looks kind of like a heart, at least one that's, fell over sideways. If you turn your head sideways to the right, it kind of looks like a heart. So that's why it's called a cardioid. Well, related to cardioids are also things called lemnicons. These are really cool names, right? We're used to things like parabolas and lines, so now we get cool names like cardioids and lemnicons. Lemnicon sounds like lima bean or something. But as I mentioned, I do lots and lots of gardening. I plant a little small variety of lima beans, of butter beans. They're really pretty good. So lemnicons are pretty cool too. So let's see what these look like. If I try plugging in 0 for theta, cosine of 0 will be 1. So I end up with 1 minus 2 times 1. That whole thing turns out to be negative 1. At theta equal pi over 2, cosine of pi over 2, well, that's 0. So I have 1 minus 0 for r. At pi, cosine becomes, well, negative 1. So I end up with 1 minus negative 2, so that adds together to give me a 3. And at 3 pi over 2, cosine is 0 again, so I'm back to just 1. And 2 pi, when I plug that in, gives me negative 1 again, like we started with. So what does that look like? This is always a surprise for students, because if you try to plot points, I don't know that you would, without knowing what's coming, draw this picture. This is super cool. I mean, look at this. This is squirrely and swings around and makes all sorts of little loop-de-loops and things. But why the loop-de-loops? What in the world is happening here? So let's think about this carefully. So here's where we start. Theta equal to 0, which means I should normally expect to see something out here on the positive part of the x-axis. Theta is equal to 0, but what's my r? Oh, r is negative 1. That means I have to go backwards by 1. That's weird. So I end up over here where r is at minus 1. Now, all the way around from 0 to pi over 2, you would think that you'd just strike out and go this way, because I need to go to the point pi over 2 as my theta and 1 as my r, which would be here. So why don't I just draw a straight line, or maybe a wiggly, curvy sort of line, but just go straight there? Well, the reason is, for the first little bit, r will be negative, because it starts out at -1. So for the first little bit, my r is negative. So as I change my angle around this way, for a little while, r was -1, it's going to stay negative. So actually what I get is stuff drawn in the third quadrant instead of here in the first quadrant. Eventually, I will get to a point where my r turns positive, and I'll swing around this way. And then, of course, as my r increases, then everything works fine the rest of the way. I go from r equals 1 to r equals 3, then from 3 back to 1, and then it repeats. It makes this sort of rest of this curly Q, because it has to go from a +1 back to a -1. So again, this little curly Q here is really weird, and it's hard to get your head around when you first see it. So maybe it's useful to draw, or to plot a few more points to convince us how this works. So when theta is 0, r is -1. By the time we got to pi over 2, r was +1. What happens in between? Well, let's try pi over 4. So at pi over 4, you plug in pi over 4 and you get 1 minus square root of 2. Square root of 2 is like 1.4-ish. So that's a very slightly negative number. So at theta equals pi over 4, which we'd expect to be plotting over here somewhere, we actually get a slightly negative number. That's why we're plotting something here. By the time our angle gets to pi over 3, oh look, cosine of pi over 3 is a half. So when I multiply that by the 2, I get 1. I subtract that from the 1, I get 0. So this point right here where I cross the origin again is actually the point 0 comma pi over 3. So at the angle pi over 3, that's when I actually cross the origin and wrap myself back around. Another really cool example of something in polar coordinates is a rose. So why do we call something like this a rose? Right, well, let's see. So if I stop plotting points, then this is what happens. I'm going to try 0, and I plug in 0, I get cosine of 0 is 1, so r is 4. But next, I want to plug in pi over 4, not pi over 2. So this is a really good place to stop and talk about why it is that in all the examples we've done so far, I've been plugging in 0, which is to the right, pi over 2, which was straight up, pi, which is straight to the left, and 3 pi over 2, which was straight down. In other words, these sort of 4 compass points, north, south, east, and west. So here I've set up my chart to plug in something in the middle, something that points off at a 45-degree angle at pi over 4. Why in the world am I plugging in pi over 4? Well, the reason is, what I really want to be taking the sine or the cosine of, I want to be plugging into the sine or cosine these 4 corner angles, 0, pi over 2, pi, and so on. So how am I going to get the cosine of pi over 2? Well, in my equation, I have 4 cosine of 2 theta. Whatever angle I plug in there gets doubled. So if I were to plug pi over 2 in there for theta, it would get doubled before it actually has its cosine taken. So if I plug in pi over 2, I'll double it and get pi. I'll actually be taking the cosine of pi, which isn't what I want. I really want to take the cosine of pi over 2, because that's where interesting things happen, is when I plug angles like pi over 2 and pi and 0 and 3 pi over 2. Those corner angles, those compass cornered angles, north, south, east, and west, those are the angles I want to plug into the cosine. So because my angle gets doubled, I back off and try pi over 4. So pi over 4, I double that and I get pi over 2 is what I actually take the cosine of. The cosine of pi over 2 is 0. Now let's try pi over 2. It gets doubled, and I'm actually taking the cosine of pi. Cosine of pi is -1, so r turns out to be -4. I try 3 pi over 4. Well, when I double that, I get 3 pi over 2. Cosine of 3 pi over 2 is 0. Let's try pi. I double that, and I'm at 2 pi. which cosine of 2 pi is 1. So r is equal to 4 times 1, or just 4. And you might think, oh, that's awesome. I landed on 2 pi. I'm done. Well, yes, we took the cosine of 2 pi, but we've actually only made it halfway around with theta. Theta is still at pi. So we've got to keep going. We got to try 5 pi over 4. 5 pi over 4 would be 5 pi over 2 that we take the cosine of, so we get 0. We plug in 3 pi over 2. That's really the cosine of 3 pi, so I get negative 1 again for cosine, or negative 4 for r. At 7 pi over 4, I'd be back to 0. Now, I didn't write 8 pi over 4 because, of course, that would get us back to 4 pi, and I've wrapped all the way back around. Okay, so you see that we've had to use a much finer scale on our thetas, right? We've checked theta much more often than we did before because we're going to get lots of loopy-loopy things happening when we try this. So what we'll have over here is a graph like this. So let's trace this guy out and see what happens. So when theta is equal to 0, I go out to r at 4. That's cool. So r equals 4 when theta is equal to 0. But now between theta equals 0 and theta equals pi over 2, sorry, not pi over 2, theta equals pi over 4, which again would be pointing in this direction. Right? By the time theta is equal to pi over 4, well, r is decreased back to 0. So that means that, here we go, start over here with our radar arm. Our radar arm is pointing out 4 units in the theta equals 0 direction, and now it has to shrink, r does, as my radar arm moves along. So now my radar arm is pointing in the 45-degree angle, but r has dropped all the way to 0. Now what do I graph next? Well, I need to take theta between pi over 4 and pi over 2. So that's this part of the angle, right? So you'd expect to be drawing something over here, and you think, oh, I'm going to draw this part of the loop, but you don't. What happens next is r goes negative. So actually, instead of drawing things in the first quadrant, I'm going backwards and drawing things in the third quadrant. So what I actually get is this part of the loop, so that when I get to an angle of pi over 2, I'm actually pointing straight down. Then I let my angle keep going, and I go from pi over 2 to 3 pi over 4. R swings back around, still negative, until it comes back to 0. Now between 3 pi over 4 and pi, r goes positive again, and so I can wrap out this point until I get to pointing at 4 units in this direction. And from there, my curve swoops around the rest of the way. It's positive. Now it's all negative again. Then it goes positive again for r as it goes this last loop. If you have a really old TI 80 something calculator that's old enough so that the processor is a little slow and it will graph in polar coordinates, you can actually see it as it draws this as it goes out. And a faster calculator, if you try it on Wolfram Alpha or something, just gives you the graph. But if you can see it actually sketch it, you can sort of imagine what's happening as I move my theta along, how the r goes positive and then negative and positive and negative. So it wraps around and makes these various leaves. So we call something like this a rose, and we'll call each of these 4 pieces there in the graph leaves of the rose. So a standard kind of question might be, find the area of one of the leaves, which we'll talk about in our next video. So one last question about how I decided what angles to try. This was cosine of 3 theta, and so I used pi over 4 instead of pi over 2 so that it would get doubled. So I was actually taking the cosine of pi over 2. How did I know to do that, or what would I do differently? If it had been, say, cosine of 3 theta, what would I have done? Well, I would have tried pi over 6. Because if you plug pi over 6 in, and I multiply the theta by 3, then the pi over 6 times 3, well, stuff cancels and gives me pi over 2. So I would still then be checking the cosine at pi over 2. All right, so next was a lemniscate. I really, really like lemniscates. They're super cool. This looks almost exactly like the rose we had before, except it's r squared equals 4 cosine of 2 theta. So another way you might write this is r equals the square root of 4 cosine 2 theta. Well, now we start plugging in numbers, and something interesting happens. So when theta is equal to 0, of course you get cosine of 0. which gives you 1, and you take the 1 multiplied by the 4, and then take the square root, you get 2. Okay. At pi over 4, plug that pi over 4 in again, so that I'm actually taking the cosine of pi over 2, which of course is 0, and square root of 0 is 0. At pi over 2, oh wow, what happened? Something broke, because when I plug in pi over 2, I get the cosine of pi, which is negative 1. So I'd be taking the square root of negative 4. Uh-oh, big problem. It's not so much that maybe undefined isn't a great word. What you really have is 2i, right? But minor rant for just a second. Calculus books studiously avoid using complex numbers. You may have noticed that we've worked really hard through all of Calculus 1 and so far in Calculus 2 to not use to not use complex numbers. This is somewhat irritating for me because, as I mentioned in the Get to Know Me video, my research area is in complex analysis. It's sort of calculus with complex numbers. Really cool stuff happens when you let yourself use complex numbers, but we don't do any of that this semester. So we will call this undefined because we'd be taking the square root of a negative number. At 3 pi over 4, cosine gives us 0 again. At pi, the cosine of 2 pi, which is 1, so I end up taking the square root of 4, which gives me 2. As I check the other points, I get 0, then I'm back to being undefined again, because I'd be taking the square root of a negative 4 when I plug in 3 pi over 2, and back to 0. So what happens is I get a curve like this. It looks a lot like the rows we had before. Instead of reaching out all the way to 4, it only goes to 2, right? Because I've taken the square root of the 4. So the biggest that r ever gets here is 2. But 2 of the petals seem to be missing. In fact, what I really got is this sort of dead zone where there's nothing happening there. That's because that's the part where 4 cosine 2 theta went negative. And when 4 cosine of 2 theta goes negative, I can't take the square root of it. So I have this dead zone there where the theta ran between pi over 4 and 3 pi over 4, and where the theta ran between 5 pi over 4 and 7 pi over 4. There's no part of the graph there. It's just undefined. But it does make a really, really awesome picture.